So I like to look at things easily because sometimes it can be really complicated to see Bohr and Haldane effect. So this is a very simplified way of doing it. You have hemoglobin. Oh, let me make it red. You have hemoglobin. Your hemoglobin can be in two or three states. There's more than this states. I'm going to just throw out 3 of them, but we're going to concentrate on 2 of them. In one state, it could be carrying oxygen, like this. All right? In another state, it could be carrying carbon dioxide. So it could be carrying it like this. It might not be exactly 4, but just bear with me for now. So let's take this first molecule over here, this molecule of hemoglobin with lots of oxygen, and let's dump it in an environment. And the environment that we're going to dump it in is an environment where you have a lot of O2. In the case that you have a lot of O2, nothing changes. Because think about it, oxygen is going to come in, it's going to hit your hemoglobin, and then the maybe this oxygen might leave at one point. So oxygen, nothing changes. Same thing happens with carbon dioxide. If your hemoglobin has a lot of carbon dioxide, and there's a lot of carbon dioxide around it, nothing changes. The thing that changes is when your environment changes. Let's say you don't have oxygen around you, but you have CO2 around you. If you have a lot of CO2 on it, you are competing against 2 states. You're competing against this state over here versus this state over here, right? Does that make sense? What happens when you have a lot of CO2 around? Your CO2 is going to come onto your hemoglobin. What's going to happen to the oxygen? I'm not going to bind there. Yeah. So when you have a situation where you have a lot of CO2, what happens to your binding of your O2? Decrease. This is known as the Bohr effect. Let's take a look at the next one. You have this molecule of hemoglobin that has a whole bunch of carbon dioxide on it. Let's dump it into a situation where you have lots of oxygen instead. Let me just make that green. Oh, I want green. And now we have a lot of oxygen. So what happens here? When you have a lot of oxygen, what does the oxygen want to do? It wants to kick it out, right? It wants to kick out your CO2. So your oxygen is going to come in, and then it's going to want to kick out your carbon dioxide. This is known as the Haldane effect. Just as a disclaimer, so that Dr. Lucero doesn't go after me, they're not completely competitive. They're actually non-competitive. They actually bind on different sites of the hemoglobin. So you can think of it as competitive just to help you conceptualize it, but it's actually non-competitive, and that distinction is not really that important here. So those are the 2 effects. How does this look in the body? So the way that it looks like in the body is this. You have a human, and I'm not going to draw it to scale very well. You have a lung over here, very small lungs, and you have your feet. Your hemoglobin is going to go from your lung, and don't smile at my, all right, so I'm going to skip the heart. I'm going to skip the heart completely. So I'm going to get this hemoglobin, it's completely oxygenated, and it's going to go to your feet, all right? So this hemoglobin, what state is it in? It's really happy, it has all its O2 around it, but what happens to us? You went to the feet. Your feet has high CO2 or low CO2? High CO2. So what do you think their environment would be? CO2 all around it. What does the CO2 want to do? It wants to kick out the oxygen. So you can think of it as the binding affinity of the oxygen is less, right? I mean, it's not binding as much because CO2 is kind of getting in the way of it. So this makes a lot of sense, because if you're at your feet, what do you want to do? You want to get rid of what? You want to get rid of oxygen from your hemoglobin, right? Is it serving its purpose? Yeah, it is. What is happening to the CO2? CO2 is going on the hemoglobin to be carried away. That works too. So what effect was that called? Is that called the Haldane effect, or is it called the Bohr effect? It is called the Bohr effect. And Bohr effect, let me just make sure that your notes are good. So the Bohr effect is if you think of it, you can think of it as the effect of CO2 on the carriage of oxygen. What is the Haldane effect? Let's take a look. This molecule over here is going to go this hemoglobin is going to go all the way up, is going to go back to your lung, is going to drop it off. So what state is it in now? It's going to have a whole bunch of CO2s carried around. What type of environment is it? Is it a high oxygen environment or a low oxygen environment? High oxygen environment. So you have a lot of O2 all around you. What is it going to want to do? It wants to kick off that CO2. So in that case, let's think about it. You went to the lung. What do you want to do? You want to get rid of your CO2. Is it following its goal? Yes, it is. How about is it filling up with oxygen so that it can go back to your tissue later on? Yes, it is. So what is that effect called? Is that Bohr effect? Haldane effect. That's the basis of Haldane effect and Bohr effect. But that's not how they're going to test you on it. They're going to test you on graphs. So let's go over those graphs. So if you guys are really good at Michaelis-Menten kinetics back in MCP2, you can think of it that way. And if you're really good at it, it'll help. If you're not so good at it, let's go over another way of doing it. So let's take a look at what these graphs look like. So these graphs kind of look like Michaelis-Menten already, doesn't it? I mean, it kind of like that sigmoidal curve. It kind of asymptotes out. Okay, so first thing, let's take a look at y-axis. Let's forget about that for now. Y-axis, what do you have in a y-axis? We're going to look at, in the case of Bohr effect, we're just going to talk about Bohr effect first. So it's going to be percent saturation of oxygen percent. Yeah, oxygen percent saturation of hemoglobin. So it's basically saying like how much of your hemoglobin, your whole entire population of hemoglobin is holding oxygen. And then on your x-axis is millimeters of mercury of oxygen. What was Bohr effect again? It is the, what was Bohr effect again?
Carbon dioxide.
Yeah, it's the effect of CO2 on oxygen. So everything that you're looking at is going to be oxygen. Just think oxygen. Let me give you a graph. This is how you read it. You pick anywhere on the x-axis. Anywhere, doesn't matter. And then you go up. And then you hit a line, and when you hit a line, you read a value. The value is going to be the amount of oxygen. You could think about like how much oxygen you have. I mean, over here you have like 100% oxygen. Over here you might have like 20% oxygen. Read it like that. Here's the next thing. What happens when you keep on increasing the millimoles of oxygen? It's synonymous to my example up above. So remember before, like I was saying, like, what if I added a whole, okay, actually it's over here. So remember when I was showing you this one over here, I said, like, what happened if you had a lot of oxygen around it? The oxygen would kind of force its way onto the hemoglobin, right? Well, in the case of here, as you add more oxygen into it, you're forcing oxygen onto your hemoglobin. It's just basically oxygen. You keep on adding more oxygen onto it. And at one point, you can completely saturate every single molecule of hemoglobin is going to have an oxygen on it. So that's what this represents. So like as you keep on adding more oxygen in your environment, you're going to force that oxygen onto your hemoglobin. So let's give you another line, and let's see if we can decipher this. So when you see another line, first thing you do, pick any spots on your x-axis, and then go up. That's one. That's two. So when you take a look at this, it doesn't matter what millimoles of oxygen you have. Just look at it in this way. When you go up all the way to this point, how much oxygen do you have? 20%, right? Not too much, right? But what if you went all the way up over here? Are you holding more oxygen or are you holding less oxygen? How much oxygen you have? 40%. Which one's higher? Is this one higher, or is A higher over here, or is it B? Which one has more oxygen at that point? A? A. Okay, A. Does that make sense so far? It doesn't matter where you pick on the screen. I'm just giving you an idea of how to look at it. So if A has more oxygen, does it mean that A has higher binding or lesser binding? Has higher. So all you have to do is higher binding. Okay, let's put another one. C. Does that have higher binding or less binding? Let's take a look. You use the same exact line, and then you go all the way to the left, and maybe this is like 10%. I'm just making up numbers over here. And so you can tell that, oh, only 10% of all your hemoglobin, it has oxygen. It's only 10% of it. Do you think it has a high binding or it has less binding? Less. Low binding. No matter what it is, Haldane Effect or Bohr Effect, you read them the same. That's how you read them. All right? You just read which one has higher binding, which one has less binding. All right? Let's take a look at it in terms of the Bohr Effect. Okay, so once again, what do? You take a look at your graph. You have one graph that goes like this, you have one that goes like that, and usually you have one that goes like this. Which one, A, B, or C, has higher binding? A. Okay, A has higher binding. How did you do it? So let me just make the percent saturation of O2 on hemoglobin. And then this one over here is millimeters of mercuries of O2. All you had to do is pick anywhere on the outline. Sorry, it's a little messy over here. Don't look at that. And all you do is look. A binds more with less oxygen than anything else. So let's try to make sense of this. Let's go back to low binding and high binding. Remember when I was telling you the story about the hemoglobin and it goes along? Let's say it went to your feet. Ooh, that's an interesting foot. Okay, it went to your foot. It's at a state where it has a lot of O2 around it. Oh no, it has O2 on it, but it has a whole bunch of CO2 all around it. Let me ask you this. The O2, is it binding very tightly or is it binding very weakly? What happens? What does the CO2 want to do? CO2 wants to kick out your oxygen. So oxygen, is it really tightly bound or is it very loosely bound if it can get displaced so easily by CO2? Low binding, right? Tell me, hemoglobin that is in your foot, that is already oxygenated like this, would it be A, B, or C? C. C is low binding of oxygen. Everything you're thinking about, once again, you're an oxygen land. Everything you're thinking about is oxygen. Does oxygen come off or does oxygen come on? So in this case, when you're at your foot, you are at low binding. So let me think. Let's write this down. Oh, I got it. When CO2 increases, binding goes down. That is the Bohr effect. However, there are other effects that do very similar things, and you can do this really intuitively. The other factors that will make the binding less binding is going to be pH, temperature. What else? 2,3 DPG or BPG. It's di or bi. It doesn't really matter. But let's just do it really intuitively. When you are at your feet, do you have high CO2 or very low CO2? High CO2. If you have high CO2, what is it going to do to pH? Down. If it's down, do you want to be releasing oxygen or do you want to be giving it up? Oh no, that's the same thing. Do you want to give up oxygen or do you want to take oxygen in? Remove it. So do you need binding to be high or do you need binding to be low? Low binding. So when your pH, like your feet, goes down, the binding of oxygen is less. Temperature. When your lungs, when you're breathing in, you're cooling it off, especially with the AC at 60 degrees Celsius, Fahrenheit, sorry, Celsius, 60 degrees, you're cooling off your lungs. Your feet should be warmer. I don't know. It's pretty cold right now too. My fingers are freezing right now. But at your extremities, they're warmer than in your lungs. So in that case, extremities, do you want the hemoglobin to release oxygen or do you want to take it up? You want to release it, right? Extremities. You want to have the oxygen available for your tissue. So when temperature goes up, what happens to oxygen binding? It goes down. So that's increase of temperature. And finally, 2,3 DPG. You upregulate 2,3 DPG when you are at really long, prolonged periods of hypoxia. So you don't have a lot of oxygen, but let me just let me just show you really quickly. Usually, when you breathe, you usually have hemoglobin, and usually it loses 1 oxygen at most. What 2,3-DPG does is that it makes it in a state where you could release more than 1 oxygen. So you can maybe like lose the 2nd oxygen, or you can lose the 3rd oxygen, maybe even the 4th oxygen. So if you can lose them easier, does that mean that you have higher binding or lower binding? Lower binding. So when you increase DPG, you lower the binding. So any of these parameters will shift this curve, this B, let's call this normal, this way. And that is called a right shift. The opposite effects will be called a left shift. So let me ask you a question. Let's say you had this woman, goes to the clinic, and then eats a lot of Tums, lots of acids, like she ate the whole entire can. What happens to your blood pH? Goes up. If her blood pH goes up, do you think that she's going to be A or C? A. Let's say you have the same exact person, and this person had lactic acidosis, diabetes, ketoacidosis. pH goes down. Which way is the curve going to go? To the right. That is the Bohr effect. Do you have any questions on Bohr effect?
Can you explain how carbon monoxide poisoning?
Yes. So let me go back over here, up over here. I had an extra one over here. So in the same exact spots as oxygen, there's going to be spots that carbon monoxide can occupy. And when it occupies it, it stays in those spots and it gets stuck there. And it's a competitive inhibitor of O2. So if you want to look at a graph for that, just think about it. Oh, there's only 2 CO2s that get stuck on your hemoglobin, right? So how much oxygen can you possibly hold? Half, right? Because half of them is filled up with CO2. Okay, so like your whole entire body, you have like, everything looks like that. And normally it looks like that. How much oxygen can you possibly hold? I mean, if you have an oxygen over here and you have oxygen over here, how much oxygen can you hold? Half as much. So in those cases, normally, if you think about Michaelis-Menten, yes, Michaelis-Menten, you can bind all the way up to 100%. But in the case of CO2, you can only go halfway. Does that answer your question?
So the left shift on the board?
It's not exactly a left shift. They don't usually talk about CO2, carbon monoxide, in terms of a left or right shift. You need to know that it looks, unless she did. Did she talk about it as a left or right? Yeah, I don't think they usually talk about it in terms of a left or right shift. But you do need to know that the graphs look different.
Carbon monoxide.
Carbon monoxide, yes.
We're saying that only 2 molecules of carbon monoxide combine to hemoglobin?
Yes. Is that correct? Or is it incorrect?
Oh, I don't know. I don't know. So can't, like, could you ever have like 3 in any situation or not?
I'm not sure if it can have 3 every so often, but like based on the graphs and the way that they drew the binding, I mean, it looks like, I can show you in the notes afterwards.
I think it could be more, but I'm not sure.
Yeah.
I think they might just use 2 molecules to just illustrate that point. But
Yeah.
it depends on
I'm not quite sure.
I can show you the graph later. I have a good image for that. But
So that would be the same thing with like fetal hemoglobin.
fetal hemoglobin? Fetal hemoglobin, okay, so fetal hemoglobin would be a left shift. And the reason why fetal hemoglobin would be a left shift, okay, so All right, that's a loaded question. So hemoglobin usually has the fetal unit and it has the alphas like that. What the fetals actually do is it prevents 2,3-BPG from binding onto it. So you remember that 2,3-DPG? What does it do? Does it do a right shift or a left shift? It does a right shift, right? Because you're putting 2,3-BPG on it so that you can release more oxygen. So the 2,3-DPG helps you release it. But now, when fetal hemoglobin goes around, you don't have 2,3-DPG. So if you don't have 2,3-DPG to help you release the oxygen, left shift.
You can also think about it in terms of the fetus is always getting oxygen from the mother, right? So the fetal hemoglobin would always have to have a higher binding, higher affinity for oxygen than what you would normally expect of an adult. So it would have to be higher affinity, right? So
Yep. Any questions still? All right, we get to Haldane Effect. So Haldane Effect looks really similar. And you know what? A lot of people get confused because Haldane Effect looks like this, right? And that's a little confusing. But think of it the same exact way as you did before. I mean, when you saw 3 graphs that were going along, what did you do? You took a random place on your x-axis and you just basically said, oh, I have, how much binding do I have here? How much binding do I have here? How much binding over here? If this is, which one of these lines, blue, A, B, or C, A, C, has the highest amount of binding? What has the highest affinity? A. Okay, same exact thing. Now I'm going to change it so it looks more like the Haldane effect, and I'm just going to draw it like that. It's just another part of the graph. I mean, we don't really need to worry about it too much. So once again, Haldane effect. Remind me again, what was Haldane effect? It was the effect of O2 on CO2. Remember, it's opposite of Bohr effect. So everything that you're going to see here is going to be in the form of CO2. You're in CO2 land. Over here, it's going to be CO2 content on your y-axis. So on hemoglobin. So once again, it's basically how much of your hemoglobin is full of CO2. It's the same exact thing. They just change it a little bit. It's not like saturation. They use CO2 content. You can think of them as the same exact thing. And then over here, on this axis, you have increasing CO2, millimeters of CO2. This is, once again, this is the environment that you're in. If you're at your feet, you have a lot of CO2 around you. If you're in the lungs, very little CO2. So once again, let's take a look at when you go to the right. When you go to the right, you have more and more CO2 in your environment. So you have your hemoglobin. Hemoglobin, it has a lot of CO2 around it. When it has a lot of CO2 around it, what happens? You're going to force your way into that hemoglobin. And then at one point, you're going to saturate. You're going to have a whole bunch of hemoglobin. Let's say we added more graphs on it. Once again, you're going to get so bored of this. Which one has higher binding? Do I need to redraw this line again? A, high binding. Let me just write high binding. And I'm going to say low binding over here. But what makes it high binding and low binding? So let's take a look. If you have a lot of CO2 on you, like this, do you think that you're going to have high binding or going to have low binding? There's no oxygen around. So the binding is going to be high because like the CO2 is going to come in, and it's going to kick out CO2. It's like you're saturated with CO2. So in this case, you can think of this blue line over here as 0 millimeters of of O2. You have no oxygen anywhere. But let's take a look. Let's say I moved you to your lungs. Your lungs have a whole bunch of oxygen. What's going to do to the binding of CO2? Is it going to increase or decrease? Decrease, because you're going to have less CO2 that's going to be bound in your hemoglobin. It's getting kicked off by this O2. So we can make a guess. In the situation where you have this much oxygen around, this like, I'll just say like 100 molecules of oxygen. You can think of it that way. You're going to have this binding. So let's say you have something in between. Let's say you have something in between where you don't have that as many oxygen like this. Maybe it's like half as much. So maybe we can have it at, let's say, 40. So what do those curves actually represent? They represent how much oxygen you have. In the case of a lot of oxygen, if a lot of oxygen, binding is really low. When you have a lot of oxygen, your CO2 is popping off all the time. Remember, we're in CO2 land. Everything is CO2. So CO2 pops off, low binding. In the case when there's no O2 around, what's the binding? Really high. So this is how we use it. This thing over here, on your x-axis, you have millimeters of carbon dioxide. There are two values you must know. The two values that you need to know is going to be at 40 millimeters of mercury, and the other one is going to be 46 millimeters of mercury. The reason why these values are important is because 40 millimeters of mercury, is that a lot of CO2 or is that very little CO2? That's very little CO2. Is that going to be your lungs or your feet? Lungs. 46, is that high? Is that going to be your lungs or your feet? That will be your feet. So this is how you read this graph. Okay, so there's another two values that you need to know. You need to know how much oxygen is in your lungs at any point. Like in your lungs, how much millimeters of mercury of oxygen do you have? 100, right? Okay, so 100. And how much do you have in your feet? 40, 46, 46, 46. Oh, I even made it, 46. Okay. So let's just connect the dots. Your lungs are over here, right? How much oxygen do you have in your lungs? 100 millimeters of oxygen. How much oxygen do you have in your feet? 46. So what this graph is basically telling you is that they gave you three conditions. They said, like, what happens to CO2 when you have no O2 around? What happens when you have a lot of O2 around, middle amount of O2? And what if you have a lot? These are experimental values. They're all experimental values. A, the black line, the green line, they're all experimental values. What they're doing is they're basically saying, like, as a person, physiologically, where do those points exist? So, like, in your lungs, you know it's always going to be 40 millimeters of mercury. And you know that it's always going to be 100 millimeters of mercury of O2. So that's this point. At your feet, you know that's going to be 46 of CO2, and then you know that's going to be 40 or whatnot of O2. So the real line physiologically is that. So the Haldane effect, these graphs, basically those 2 points over here represent how the curve would look like for a normal person that's not experimental. Like all those lines, they're experimental values that show you like high binding and low binding. And if you think about it in terms of, remember I was talking to you about how your feet, let's take a look. Your feet has a lot of CO2 or very low CO2? High CO2. If it's high CO2, would the CO2 binding be higher or lower? It would be higher. Lots of CO2 forcing onto the CO2. Look at it. This point over here, is it closer to curve A or curve B? It's closer to curve A. It's binding tighter. How about B, when you're in the lungs? How's the CO2 binding? Is the CO2 binding very well or is it binding very little? Just think of it conceptually. If you're in the lungs, you have a lot of O2 around. All the O2 is going to kick out your CO2. So your CO2 binding is going to be low. Look at it. Is it closer to B or is it closer to A? It's closer to A. A, we said, was low binding. So that's how you read these graphs. You guys have any questions?